Hey everyone, so today we're going to be doing another AP Calculus BC free response question. So this one is also from the 2018 AP exam, just like the one we did last week. But this one is question 6 of the non-calculator portion. Once again, I'll have the link below and you can check that out there if you'd like. Okay, so let's dive right into it. This problem is all about Taylor series or MacLaurin series. Okay? So basically, what we're told is they've given us the MacLaurin series for ln of 1 plus x, right? And it's this guy right here. And now we're defining this function f to be this guy here, x ln of 1 plus x over 3. All right, so the first thing we're being asked here is to write the first four non-zero terms and the general term of the MacLaurin series of f, right? Or this guy right here. First thing I want you to notice is how similar this guy looks to that guy. Right? So they look pretty similar, right? In fact, the only difference is that instead of plugging in x, we're plugging in x over 3, and we're multiplying the whole thing by x. So I'm going to do a little bit of fancy footwork here, and please try it, and I hope you're able to follow along. Right? So the first thing I'm going to do is I'm going to define this function g of x to equal ln of 1 plus x, right? Which we already have a MacLaurin series for. It's been given to us. Okay. Now, given this, what changes do we make to f of x to reach g of x? Well, we just multiply by x and plug in x over 3, right? So given that, we can reach the conclusion that f of x is the same thing as x times g of x over 3. Sweet. And I already have a MacLaurin series for g of x, right? And so I could use this MacLaurin series for g of x, plugging in x over 3, multiply that by x, and I will have my MacLaurin series for f. So I hope you followed the game plan there. We want to plug in x over 3 into this MacLaurin series, and then multiply everything by x. So let's go ahead and do that. So we can now say that f of x is equal to x times, let's plug this stuff in. So we're going to start with just x over 3. Okay. And then plus, sorry, that should be minus. So it'll be minus x squared over 2. So we're going to have x squared over 3 squared, right? Because remember, we're plugging in x over 3 divided by 2. Okay. Then plus x cubed over 3, which is going to be and I hope you realize this is the same thing as x over 3 cubed. Right? I'm just distributing the power just to do one step extra. Okay, so we have that over 3, yeah, and then minus x to the 4th over 3 to the 4th over 4, and then plus yada yada yada. And now we will have the negative 1 to the x. So this, and now we have to deal with the nth term here. Okay, so the negative 1 to the n plus 1 does not change. Right? So that's still going to stay the same. But what does change is the rest of it, right? Because we no longer just have x to the n, right? But we have x to the n divided by 3 to the n. Right? You can kind of see we have 3 to the first here, 3 to the second here, 3 to the third here, 3 to the fourth here. So we're dividing that. So we have x to the n. We're dividing that by 3 to the n. And then we have just times the n there, okay, which we already have there. Okay? And now we can just distribute the n to all of these, and we'll have our final answer. So our final answer is going to be, we'll have x squared over 3 minus x to the third over 3 squared times 2 plus to the fourth over 3 cubed times 3 minus x to the fifth over 3 to the fourth times 4. And you can now see when we're calculating this nth term, the only difference between these two now is that instead of x to the nth, I'm going to have x to the n plus 1, right? Because if you notice, this is 3 to the fourth, but that's 3x to the fifth. So the x's are 1 power ahead of everything else. So we're going to have the negative 1 to the n plus 1 is going to stay the same. But now we're going to have x to the n plus 1, right, over 3 to the n times n. And that right there would be your final answer for part A. Sweet. All right, so now let's take a look at what part B is asking for. Right? So part B is saying, determine the interval of convergence of the MacLaurin series for f, which we just found down there, and show the work associated with that. Okay, so basically what it's asking for is to find the interval of convergence of this infinite sum from n equals 0 to infinity of negative 1 to n plus 1, x to the n plus 1 over 3 to the n times n. Try to find the radius of convergence of that guy. Okay, we want to find the radius of convergence. Now, typically, whenever we are looking for a radius of convergence problems, we like to do either a root test or a ratio test, right? At least in the beginning, because those give us a very nice radius to work with, just by the nature of the test. Okay? So in this case, I'm going to go ahead and use a ratio test, just because the ratio test, I think, will cancel some things out just a little bit nicer than a root test will. Okay, so let's go ahead and use a ratio test. Okay, we're going to use a ratio test. And basically what we're doing with the ratio test, we're taking the limit as n goes to infinity of a of n plus 1 over a of n, and the absolute value of this guy. We're taking this limit here, and let's go ahead and do that. So we will have the limit as n goes to infinity of a of n plus 1, which is just going to be the next term of this. So we will have, my absolute value bars there, negative 1 to n plus 2, x to the n plus 2, 3 to the n plus 1 times n plus 1 times, now instead of dividing by a of n, I'm going to multiply by the reciprocal of a of n, because that will make things just look nicer. Also, I avoid having multiple layered fractions, and also just makes the cancellations look better. So we will have all this times 3 to the n times n over negative 1 to the n plus 1 times x to the n plus 1. Cool. So now we can go ahead and do some cancellations before we evaluate our limits. So firstly, the negative 1 to the n's just disappear because we have written an absolute value. The negative 1 term just doesn't show up inside an absolute value, so that's done. Next, this 3 to the n plus 1 and this 3 to the n cancel out. And what that leaves you with is actually just going to be a 3 to the first here. Right? And if you're confused as to how that works, just think about it. 3 to the n plus 1 is the same thing as 3 to the n times 3 to the first, right? And so basically what's happening is this 3 to the n is canceling out with this guy here. So this is the one that goes away, so you're just left with that 3 to the first there. So that's how that works there. Okay? In the same vein, this x to the n plus 1 is going to cancel with this to the x to the n plus 2, and we're just going to be left with an x to the first over there as well, right? So all said and done, what we're going to be left with is we're going to have the limit as n goes to infinity. The absolute value still stays. We're going to have an x times n over 3 times n plus 1. Okay, cool. Now, the limit here only concerns n, right? So what we could do then is we could take this x here, right? So we see that this x and this 3 here are not really affected by that limit there, so we can bring them up to the front. So we can rewrite this as absolute value of x over 3 times the limit as n goes to infinity of n over n plus 1. So we'll keep that in absolute value. Okay. Sweet. And now we can actually evaluate this limit here. Okay. You can actually evaluate this limit. Now that's going to be an infinity over infinity limit, so you could theoretically use a L'Hopital's rule, or you could, use the Calc 1 method, divide by highest power. Either way, you're going to get that this limit simply goes to 1. Okay, this limit here is going to go to 1. So if that goes to 1, this would just come out to 1/3 times the absolute value of x. That's just because, and we can take this out of the absolute value because the absolute value of 3 is just 3. Okay. And now we have a couple of different things that would happen. If this entire quantity, right, if this entire quantity is less than 1, the series converges. Right? If this entire quantity is greater than 1, the series diverges. If this entire quantity is equal to 1, then we are inconclusive. Right? Because the ratio test is inconclusive when the limit comes out to 1. Okay? So we want this first case to be true. Right? We want to find only where this first case is really happening. So let's set this guy less than 1. Right? So let's set 1/3 absolute value of x to be less than 1. And if we multiply both sides by 3, we get that the absolute value of x has to be less than 3. So this is the first part of where our series will converge. Okay? But there's one other thing that we need to consider. That's the first place that we need to think. But there's another thing that we need to consider, and that is what would happen if this thing is equal to 1. Because theoretically it could converge there, right? It's just that the ratio test cannot tell us that, but it could converge there, right? So we need to investigate that as well. And so if we multiply both sides by 3, we get that the absolute value of x is equal to 3. In other words, x is going to equal plus or minus 3, right? So we need to check each of these cases, right? We need to check each of these cases in the original series to see whether or not the series is going to converge. So we're going to check these in the original series. Okay, so let's go back. Let's go up here and do that. So let's start with x equals 3, and maybe let's do that in red. Let's start with x equals 3. So if we go back up to our original series, so that's basically what our original series is. So we'll have the infinite sum 0 to infinity of, let's see, we'll have negative 1 and plus 1 times not just x, but we're going to have 3 to the n plus 1 over 3 to the n times n. And now, just like we did previously, this 3 is going to cancel out with this guy, leaving us with just 3 to the first. So what we're going to end up with is we'll have sum from n equals 0 infinity of negative 1 to the n plus 1 times just 3, right? No exponent on it whatsoever, over n. Okay. Cool. Now that's an alternating series, right? So this is an alternating series. Okay. So I can use an absolute, I'll need to use absolute, I can check for absolute convergence by taking the absolute value of this and using one of my tests. Right? So let's take the absolute value of this guy and see what happens. So if we take the absolute value of a of n, which our series is, that's going to give me, this thing is just going to go away. So that's just going to be the sum from n equals 0 to infinity of 3 over n. That diverges. I hope you see that it diverges, because that's a p. This would be a p series with p equals 1, which diverges. Right? So we could say right off the bat that this guy right here, maybe let's do that blue, this diverges by p test of p series. Right? So this diverges, and so our series does not converge absolutely. However, right? However, if we look back to this original series, we can see that the limit as n approaches infinity of a of n is still equal to 0, right? Because it's a constant over n, it's still going to be 0. So even though it does not converge absolutely, this guy converges conditionally by alternating series test. Sweet. So therefore we can say that, okay, x equals 3, we're good. We converge at x equals 3. So that's that. And now next let's go ahead and check x equals minus 3. We need to check that. So coming back up to our original series up here, what we would have again is we would have sum of negative 1 to the n plus 1 times, we have negative 3 this time to the n plus 1 over 3 to the n times n. Okay. And now notice that negative 3 to the n plus 1 is just negative 1 to the n plus 1 times 3 to the n plus 1. So we can rewrite that as like that. So we would have negative 1. And we're being a little bit extra here, but I hope it helps. So we have negative 1 n plus 1 times 3 to the n plus 1 all over 3 to the n times n. Now these negative 1 to the n's are both just going to go to 1, right? Because they just go to 1, because if you combine them, if you could basically combine them into under the same exponent, you would get that they become a positive 1. So that's just going to go to 1. And then we can repeat the same procedure we did above, right? So this 3 to the n and this one are going to cancel, leaving us with just 3 to the first, leaving us with just the sum as n goes to infinity of 3 over n. Right? And if you recall, that's the same thing we had over here. So once again, this guy is going to diverge by the p series. Right? So this guy diverges by p series. Right? But however, this time there's no question of conditional convergence, right? Because this is our series, right? This is not the absolute value of anything like we had above. So there's no question of conditional convergence here. This is just diverges, period, right? So this guy right here is just, maybe let's just add it over there. So this diverges, right? So what's our final conclusion? Well, if we put all this together, I know we've come quite a long way since we were up here, right? So if we put all this together, what we've got is that the series converges when the absolute value of x is less than 3, or in other words, it converges when x is between plus or minus 3. It converges on this interval here. It also converges when x equals positive 3, right? However, it diverges when the absolute value of x is greater than 3 or when x equals minus 3, right? So putting all this together, we're going to get that our interval of convergence is just going to be from negative 3 x 3. So this guy right here would be our interval of convergence. And if we're looking for the radius, that's just going to be 3. So that would be the final answer there. All right, so now we can talk about part C. Now part C, if we look up here, is basically saying, all right, so let P4 of x be the fourth degree Taylor polynomial, right, of f about x equals 0. We want to use the alternating series error bound to find the upper bound for this thing right here. So we're finding the error associated with this fourth degree Taylor polynomial. Because remember, the Taylor series tells us the perfect approximation of whatever value we're looking for. If we shorten that series to like a polynomial of n terms, there will be some error associated with that. We're being asked to find that error for a fourth degree Taylor polynomial. Okay, so let's see what we can do. So if we come down here, we'll realize that so this guy right here is our series, right? So let's just bring that series down here. So once again we have the series from n equals 0, infinity, x to the n plus 1 over 3 to the n times n. Okay, so that's our series there. Now what I want you to realize is we're looking for the error associated with a fourth degree polynomial. A fourth degree Taylor polynomial. This means that we have x to the fourth as our highest power. Notice here though that we have an x to the first term in this summation here, right? We have an x to the n plus 1. So really, this fourth degree Taylor polynomial corresponds to the third term in our series. Right? This is going to be the third term in our series. Why is that important? Well, you'll see in just a second. So now let's talk about that error term. Right? So this error term, right? So the general Lagrange error multiplier, Rn of x, right? It has a very complicating formula, but effectively it's going to come out to the n plus first term in your Taylor polynomial, right? So this is basically the error associated with a Taylor polynomial with n terms. This is just going to be the n plus first term. It's going to be your error. Okay. So now we know that we are looking at a thing with 3 terms, right? So therefore, we want to find the fourth term, right? So if we look at this for our case, our 3 of x is going to be the fourth term in the Taylor polynomial. I hope you follow my logic here, right? So we know that the error associated with a Taylor polynomial of n terms is the n plus first term. This Taylor polynomial has 3 terms because it's a fourth degree, and we have the n plus 1, which means it has 3 terms. And so therefore, we are looking for the fourth term to give us that error. Okay. All right, so now that we have this, we can go ahead and actually find this fourth term, right? So R4 of not x, but it's actually going to be 2, right? Because if you remember the original statement here, it was evaluating the Taylor polynomial at x equals 2. So it's really going to be this. And this is going to be equal to the fourth term. So we're going to plug in n equals 4 over there. So -1 to the 4, 4 plus 1 times 2 to the 4 plus 1 over 3 to the 4th times 4. And when we're considering error, it's really just like a magnitude. So the sign really does not matter to us. So we can just take the absolute value of this. So the sign is just basically irrelevant. That means that this thing just goes away. It just becomes +1. And then we can evaluate the rest of this. So 2 to the 4 plus 1 is 2 to the 5th. So we will just have 2 to the 5th. And then you would have that 3 to the 4th times 4. Okay? Because remember the negative, and the absolute value just drops out because all of these are just positive numbers. Okay? And now we can do a little bit more simplifying. So you'll realize that this is just 2 squared, right? So that and that will cancel out to give you just 2 to the 3rd, right? So what we'll be left with is 3 to the 4th over 2 to the 3rd is just going to be 8, right? So we have 8 over 3 to the 4th. 3 to the 4th is basically the same thing as 3 squared times 3 squared. So we'd have 8 over 3 squared times 3 squared. 3 squared, if you realize, is just 9. So 9 times 9, we're going to have 8 over 81. And that right there would be your final answer. So yeah, I hope this helped. The thing I like about these questions so much, they integrate a lot of different concepts. So in this video, in this problem itself, we explored so many different things. So we explored P-series, we explored the ratio test, we explored MacLaurin series, we explored error bound, and yeah, I think that about encapsulates it. So it's a very broad problem. Took a while to film this, but yeah, I just hope it helps. It might be kind of long, but I will put a table of contents on there so you can check out whichever parts interest you. But yeah, thank you so much for watching, and I hope this was helpful.
If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time!